Okay, so just to um, set the stage a little bit and warn you all, um, today, this course is ultimately about Newtonian dynamics. Newtonian, yeah. It's about Newton's laws. Ultimately, we had to build up some tools to be able to deal with forces, and that was ultimately all the work we've done so far, talking about kinematics. When a force is applied to an object, the result is acceleration. Acceleration will be motion. And so we had to figure out how to talk about motion and have these equations of kinematics that give us some tools to deal with motion. That was all setting the stage for what we're going to be talking about today, which is Newton's laws, after Sir Isaac Newton. So today's big stuff, pretty cool. In some previous textbooks that I have taught out of, Newton's laws were presented in one single chapter, such that, like, you have chapter 1, chapter 2, chapter 3, chapter 4 was enormous. And so this textbook that we're using, which is free online for you, I hope you're making use of the resource to help you learn to, there's worked out examples in the chapter. There's a student solutions manual. There's a bunch of free stuff associated with this book. So I think in life, people tend to be like, oh, you get what you pay for. And if something's free, you kind of devalue it, kind of almost subconsciously. And this textbook was a project, grant funded. The authors who contributed to making this textbook did get paid. It was peer reviewed extensively to come up with a good quality textbook that is accessible to you for free. And so don't devalue it. It's a gift to you from the good people of OpenStax, and they've come up with a number of textbooks for different subjects, but they went for, I think, the most expensive, most purchased kind of textbooks right away. And there are so many textbook publishers that are desperate for my business, that want me to assign you, a $220 textbook to take physics 1 and 2. And, at least it lasts for multiple semesters, but it's just a ton of money. And, especially these days, I don't want to be sending people, at least this past year, didn't want to be sending people to the bookstore to lay their hands on something. So there's so many good things about this textbook. Please take advantage of the good stuff there. So this textbook, amongst its other qualities, does divide the chapter 4 material. Chapter 4, the Newton's laws material, chapter 4 is Newton's laws, chapter 5 is applications of Newton's laws. So we get to kind of have this even flow of material. So today is Monday. We're here together. On Wednesday, I have some dreadful all day long meetings that I really have to go to. So our Wednesday time will be asynchronous. I have uploaded a video of the lecture time and the quiz is there for you, and also a video of me going through the football question, which is the most important, includes the most important thing ever, resolving X and Y velocity vectors. So there's some stuff there for you. Ultimately pointing out that 1 week from Wednesday, on Wednesday the 16th, we do have exam number 1 on chapters 1 through 5 material. I know it looks like, you know, we are spending a lot more time building up to exam 1, and then we have a really short time before exam 2. But we kind of had to start from not moving at all, start from rest when we have been building up to exam 1, but we're kind of in the groove as we move forward to exam 2. So it's not quite as, you know, rushed as it might seem. All right, let me move some things around on my computer screen. And every now and then, so the lecture on Wednesday, which is a you know, recording of a lecture from before, whenever I rewatch myself doing a lecture, I just cringe the whole time. So I hope you never have that experience yourself, having to watch yourself do a lecture. I want to share with you our Canvas page. Here on our Canvas page, we do have a tutor for this course. Her name is Noelle Wood. She is also tutoring General Chemistry 1. She's actually a, you know, in-person SI instructor for General Chemistry 1 right now. So she's probably not available right at this moment, because I think she's actually in Meyer Hall in a room working with students. But she does have these online tutoring hours available through TutorTrack to work with you. She, I will share her email address in a message to you all later. She said if students want to reach out to her individually, because the times she lists as available for tutoring don't match your availability, then maybe something else can be found. My son did tutoring over the past year, and it's all kind of weird. You as the tutor putting your hours that are available. Just, you know, you're kind of guessing, you know, okay, well, these are some convenient hours for me. I'll put them in. Students then log in and say, okay, I would like to meet with you at this time. And it all kind of goes that way. But, you know, there are perhaps other hours that would work. They're just kind of guessing as to what hours might be convenient for you. So, but you have to do it through the TutorTrack system so that it can all be tracked and monitored. The tutor does get paid for the hours that they tutor, but you're not doing the paying. So, you know, do take advantage of this resource that Salem State is providing to you. And I don't know when a good time to meet would be. So what I have done is I've gone into the system and I've provided these blocks of time when I can be available. Oh, sorry, the phone's ringing. I think the city of Salem is telling about a cooling station. The city of, no. Yeah, it is the city of Salem. Train of thought is all gone now. Through Navigate, I have set up times when I can be available in the morning or in the afternoon. You go in through the system, you sign up for one of the available times, and then I think it's like a day or two ahead. So then I can, rearrange whatever else I was going to be doing that day to like make sure that I'm available. But I'm available to you for one-on-one meetings. Let me take care of this. Sorry about that. So I am available to meet one-on-one. Just sign up for a time and we can do that. Our Wednesday class is asynchronous, so the lecture you can watch at your leisure. The did I just double copy the football question? I'll have to go get that lecture for you. It looks like I did the football question twice instead of the chapter 5 lecture. So I will post the lecture here, not the football question twice. And then the quiz you can do at your leisure. I am still making my way through the pages to update them to this semester's dates instead of last summer, but it is my belief, let me do student view if I can find it. I have to do it here. No. Student view. It is my belief that if you want to knock yourself out and click on pages, view all pages, you will see ultimately week 4, week 5, week 6. If you want to look ahead, you can click on these and it has the materials that will be there for you in the upcoming weeks, the PowerPoints for the next chapters and all that stuff. Those materials exist. I just need to update the page with the correct dates and the proper links for quizzes and stuff in there. But that material all exists for you as a resource. When I wasn't on student view, you can see that I am desperately behind in grading stuff. I have every intention of catching up. It's been some crazy days with just family stuff. Nothing bad, just busy. And I went to 2 cookouts in a row, Saturday and Sunday, kind of, obligatory participation. But yeah, so. Okay, and my son had a bunch of friends over the house yesterday and they played games all day. It was a long time. Okay, stop share that. Move into the PowerPoint, which must exist somewhere. There it is. Let me view, reading view. Oh. I'm getting there. Share screen. PowerPoint. Share. Make it big. Okay, I am not logged into this as I normally am. I have to update my page. Yeah, it's not going to happen right now. So I think you're looking at the PowerPoint. Let me just double check here. New share. Share. Okay. Chapter 4, Dynamics, Force and Newton's Laws of Motion. That's where we're moving now. This the thing that the whole course is about is Newtonian mechanics. That's the word that I couldn't find before. Mechanics comprised of both kinematics, understanding the motion and what's going on with motion, and then dynamics, what's causing the motion. So Isaac Newton, was he just in the right place at the right time as science was being understood in a certain way that it could be organized and presented in kind of one collective body? For most of human history to that point, there was kind of the terminology natural philosophy, which, you know, a structured way of thinking, which is relevant to how we understand science now. But Isaac Newton took some different ideas that had existed for hundreds or 1,000 years and put them together in an organized way such that he's, you know, got this credit, you know, we're calling it Newtonian mechanics. He's been credited with kind of putting together a understanding of how things work, at least on a relatively large scale. I think I mentioned before briefly, when you get really, really small, Newtonian mechanics stop working and you jump into the world of quantum mechanics, where the rules are a little bit different. But the rules that we are exposed to in this course are the rules that work for almost everything we interact with, that we can appreciate that we're interacting with. Obviously, we're interacting with atoms and subatomic particles in a way, but truly, if you can hold it in your hand or, you know, drive your car or anything, that's all Newtonian mechanics are in play. That's the stuff that we appreciate that we're dealing with. Isaac Newton is credited with either co-discovering or co-inventing calculus. Calculus is a branch of mathematics that deals with things changing, and it requires a little more robust kind of mathematical calculation to address something where change is taking place. This course is algebra-based physics as opposed to calculus-based physics, which often means that we just jump to the punchline. We jump to the piece of the information where we don't need to, you know, do a derivative or an integral. We'll just take the answer and use that to do our work. Truly, for Physics 1, you don't use a lot of calculus. It's more of a Physics 2 thing. So Aristotle in 384, who lived back in the 300s BC, BCE, noted correctly, I will say, that If you push something, if you push a rock sliding on a flat surface, it moves. And if you stop pushing it, it stops moving. And if you push it, it moves. And if you stop pushing it, it stops moving. And so there's an entirely reasonable conclusion that in order for something to move, you need to be applying a force. And then not too long before Isaac Newton was active in the game, Galileo, who did a little more work with astronomy and looking at celestial bodies moving around, in order to try to explain what's going on as you're noticing the moon orbiting the Earth, or making note of other planets orbiting the sun, and there's motion for these massive objects, and like where is that the force coming from? Galileo extrapolated back and did some experiments here on the surface of the Earth and said, you know what? We've got this nice, smooth, polished marble floor and a rock, or some object on the surface of the marble floor. And if I push it, it moves. So there's the Aristotle understanding, force needed for motion. But if I give it a really good shove, it'll keep moving for a while until it slows down and stops. And the smoothness of the marble floor has a direct correlation to how far something will slide once I give it a good shove. And so maybe, just maybe, the natural state of motion for an object is moving at constant velocity. And there's this thing called friction that causes it to slow down and stop. But that's another force. That friction force is causing it to slow down and stop. But in the absence, if you use your imagination that perhaps there could be a state where there is little to no friction, it would keep going. And so maybe the natural state of motion for an object is constant velocity in the absence of friction, air resistance, all that stuff. So physics lab this week used to be very loud. I've been at Salem State for something like 20 something years. But when I first started, these air tracks were in the physics lab and were still being used. And what you would do, if you've ever played air hockey, you turn on the table and a pump is there blowing air out through the holes on the table, and the air hockey puck kind of floats on a cushion of air. Well, it was essentially like that. We would have these shop vacs, which are canister vacuum cleaners, where you can connect the hose to one side and it, is taking in whatever's out there, or the other side and it's blowing out. So we'd hook it up to the blowing out side and hook it up to this track, and we'd have a cart that would float on a cushion of air, essentially zero friction. And we could do some experiments to see what happens with motion in a low or, essentially zero friction environment. And so keep that in mind, keep that image in mind, that we do have the ability to have an instance where there is little to no friction. Okay, Newton's first law of motion. There's 3 laws, Newton's 3 laws. We will tackle those. There's both a conceptual piece, and then sometimes there's an equation that we're going to deploy. But we get a new thing now. So far we have meters for displacement, meters per second for velocity, meters per second squared for acceleration. And then in those things is time. We have these 5 kinematic variables. Those are what we've been using that are all kind of tied into acceleration, velocity, and time. But there's another thing, there's several other things, but there's another thing that we need to keep moving forward here. That is tied into this concept of inertia. So if you've heard of Newton's laws ever in your educational career, you have perhaps heard this idea: an object at rest tends to remain at rest, an object in motion tends to remain in motion. That's a simplification, but that does get the gist of the idea of across. An object at rest remains at rest as long as no net force acts on it. Net force is represented with the sigma sum sign because there can be there's almost always multiple forces acting on an object, and we need an imbalance of those forces, because typically I am sitting here on a chair. There is a force directed down toward the center of the earth. If the chair wasn't here, I would fall down to the floor. So there's a force pulling me down. We typically talk about that like gravity. Gravity's pulling me down. But there's another force that we don't even think about very often that must be pushing me back up. Otherwise, I would be falling down. And so there are multiple forces acting on me right now. If those forces cancel each other out, then I am an object at rest, remaining at rest, because there's not a net force acting on me right now. And likewise, an object that is moving with constant velocity will continue to move with the same speed. Velocity is both magnitude and direction. Velocity is a vector, speed is a scalar quantity. Velocity implies a certain speed and a certain direction. And so with this Newton's first law, an object moving with constant velocity continues to move with the same speed and in the same direction as long as no net force acts on it. So again, that idea that when it's moving, there's forces acting on it, but they're in balance. And once you change that balance, the speed will continue. If I'm driving my car down the road at 30 miles per hour, there is a force propelling me forward that's coming from the engine of the automobile, making the tires rotate, all that stuff. There's a force pushing me forward. There's also a force pushing against me to slow me down, air resistance, friction, that kind of thing. So if I am moving down the road at 30 miles per hour, I'll continue moving down the road at 30 miles per hour as long as there's no net force. There might be a net force if I step on the accelerator and I choose to speed up, then there's a net force and my speed, maybe my direction will change. If I pop the car in neutral, then the engine's not propelling me forward anymore, and I would discover that I would slow down because air resistance and all that stuff. So just that idea. So that idea of inertia, there's a quantity, there's a quantity that every object has that we represent as mass in kilograms. That represents how much force it takes to change its state of motion. So I don't know what the best example is here, but if somebody tosses a ping pong ball to you, you catch it. it didn't take that much for you to change the inertia of that ping pong ball. It was moving toward you, you reached out your hands and caught it, and it stopped moving. Whereas if somebody took a bowling ball and tossed it to you, it would take more, because it has more. The bowling ball has more of something than the ping pong ball. And what it has is more inertia. For the same velocity, the bowling ball has a lot more something than the ping pong ball does. And so that inertia thing is represented, quantified as mass in kilograms. So that's Newton's first law. Newton's second law kind of takes it to the next level where we can discuss this stuff. That, all right, so object at rest tends to stay at rest unless there's a net force. Object in motion tends to stay in motion, same speed, same direction in a straight line, as long as no net force acts on it. So that begs the question, all right, you keep talking about the net force. What happens when there is a net force? And so when a net external force, wait, there's another word there. What is that about? External force is a force that is external to the thing that is being acted on. So if your car breaks down on a level surface driving down the road and your car is not moving, you can put your car in neutral and potentially push your car over to the side, you know, somewhere safe, right? You can push your car. But if you're sitting in the driver's seat, pushing on the steering wheel, the car doesn't move. Why? Because you're an internal force with the car. You're sitting in the car, you're pushing. Turns out the car is pushing back on you and nothing's happening. Whereas if you put the car in neutral and get out of the car and then push, you are providing an external force, a net external force, I hope, if you're able to push hard enough on this massive car. So when a net external force acts on an object of mass m, the mass of the car, the result is acceleration. And the acceleration that results is directly proportional to the net force. That makes sense, right? You push harder, it moves, it accelerates more. Like that, you know, conceptually works pretty easily. And has a magnitude that is inversely proportional to the mass. That's a little bit trickier because when you say inversely proportional, you're like, what? But if the car is not very massive, if it's a light car, you push it with the same force, it will accelerate more. Whereas if your friend insists on sitting there in the passenger seat while you're trying to push the car, that will take more force from you to get it to move because there's more mass. So same force will have less acceleration if there's more mass. Same force will have more acceleration if there's less mass. The direction of the acceleration is going to be the direction of the net force, the resulting force. So this Greek letter sigma is the sum of all the forces. There can at any point in time be forces in both the y-axis and the x-axis, but typically we're just talking about one or the other at a given point in time. Net force equals mass times acceleration. Now, when people show up to take physics for the first time, if they've heard of one or two physics equations in their life, it's usually E equals mc squared and then F equals ma. F equals ma, net force, May the force be with you. You know, you may have heard of this before. We're going to be using it in equations. The thing that we're doing is mass in kilograms times acceleration, meters per second squared. When you put those together, kilograms times meters per second squared, those have been named after Isaac Newton. So that's a Newton, 1 Newton of force. So we use capital N to represent the product of kilograms times meters per second squared. So a constant force is exerted for a short time interval on a cart that is initially at rest on an air track. So this is the thing that I was representing to you earlier about the shop vac hooked up to the track and the cushion of air. So friction is negligible here. So we have the force giving the cart a certain final speed. Then we take the same force and exert that force for the same length of time on another cart. This other cart is also initially at rest, but the second cart has twice the mass of the first one. The final speed of the heavier cart is 1/4, 4 times half, double, the same as that of the lighter cart. I bring up this question to introduce the following. When we're trying to assess the final speed of the heavier cart, we would look to our equations of kinematics and we'd say, okay, so I know the initial velocity is 0, and that equals, V equals V naught plus acceleration times time. I don't right now have any direct mechanism for assessing the acceleration, but this problem has told me right out of the gate that the initial velocity was 0, so I can do something with that. And it's for the same length of time, so time isn't changing. The difference in the final velocity between the light cart and the heavy cart is to be revealed in which one had greater acceleration. Well, we know that force equals mass times acceleration. Therefore, we know that acceleration equals force over mass. Just rearranging the Newton's second law equation, acceleration equals force over mass. And I know that force was the same for both of these. The same force is exerted, same length of time. But the difference between the two is the mass of the cart. So rearranging this equation, final velocity equals the initial velocity, which was 0, plus force over mass times time. Everything else is the same except for the mass. Mass is in the denominator. So in one case, and if you have trouble kind of handling this all conceptually, nobody said you can't make up numbers, right? You have to follow the rules, but you could make up numbers and say, the mass is 1 kilogram, the time is 1 second, if that makes you happy, or the force is 1 Newton, the time is 1 second. So in one case, if the force is 1 Newton, the mass is 1 kilogram, the time is 1 second, this is 1. In the other case, where the cart has twice the mass of the first one, force is 1 Newton, mass is now 2 kilograms, 1 divided by 2 times 1 is 1/2. So I guess that gave away the answer. The final speed of the heavier cart would be half that of the lighter cart, just by doing something, either conceptually figuring out the equation, or making up sample values to plug in to use. you can come up with a decent sense of what's going on there. Similarly, constant force exerted on a cart that is initially at rest on an air track. Friction between the cart and the track are negligible. Force acts for a short time interval, gives the cart a certain final speed. To reach the same final speed with a force that is only half as big, the force must be exerted on the cart for a time interval that is 4 times as long, twice as long, equal to half as long, a quarter of that for the stronger force. And so again, we're using kinematics equations. We're trying to figure out the thing with the acceleration that will give us the same final speed, but now the force is only half as big. And I don't know if I told the story about my wife being conflicted over whether to go get a PhD in chemistry or go to medical school and become a medical doctor. As she was trying to figure things out, she did pay for and take a Kaplan course, which helps prepare people to take the medical college admission test, the MCAT. And she discovered that on the MCAT exam, at least at that time, as she did practice exams and stuff, her best strategy for answering the physics questions on the MCAT practice exam and then on the real exam was to go with the answer that was the most counterintuitive, which is sad that the people that made the exam put enough distractors and confusing things in the question that wound up being a decent strategy. I do not aspire at all to have that be the case with you guys. Rarely do I do multiple choice answers because I think I can get a better sense of your understanding of the material if you actually do a calculation and show me the steps in your calculation process, all of that. But, you know, right here, like I think when you're like, okay, so if the force is half as big, then I think you got to push it for twice as long. Like that makes sense to me. And, you know, it is the intuitive answer, I think, is the right answer for a lot of this stuff. So I'm not trying to trick you. If something does strike you as tricky, you know, please ask about it and we'll try to figure out. Everybody comes into every interaction and situation with some preconceived notions. And one of those things with physics is we really should have a decent sense of how the world works, right? You push something, it moves, it doesn't move, whatever. Like you should have a decent shot at having an intuitive understanding of how things work, but it's easy to get tripped up or to have experienced some sort of situation where you're like, oh, well, I think that's going to happen, so that's probably not going to happen. It's probably going to be just the opposite. And I don't want that to happen to you. All right. Mass represents the quantity, the quantitative measurement of how much inertia an object has. Inertia being the thing that we're talking about when we say an object at rest tends to stay at rest. How strongly does it want to stay at rest? How much motivation does it have to stay at rest? Well, that depends how much inertia it has. And that is represented in kilograms. weight is different from mass. Weight is a force and it's measured in newtons. I think that's probably doesn't matter what system you use to represent weight, because here near the surface of the earth, we're just used to a very close connection between mass in kilograms and weight in newtons. Like they're just related. And then here in the United States, we might, talk about pounds, and pounds is weight. It's a force as opposed to the mass of something. So weight is a force measured in newtons. So since force equals mass times acceleration, that means weight equals mass times acceleration. So if you're sitting still, you're weightless. You don't weigh anything if you're not actually accelerating. And no, that's not true. So this is one of my early PowerPoints, and my art perspective is terrible, but just have some patience with me. Weight is mass times the acceleration due to gravity. The weight that an object has is directly proportional to how much mass it has. And because most of the stuff that we do here near the surface of the earth, right around sea level, would tell us that this object, this 10-kilogram box that comes flying down out of the sky, has weight. It's a vector directed down toward the surface of the earth. And this 10-kilogram box, being directed downward in the negative y-axis, has an acceleration downward or an acceleration of negative 98 newtons as it falls down to the table. But it's not falling down anymore. It's sitting there on the table, sitting stationary on the table. So there's another force, because we said inertia, that an object at rest as long as no net force acts on it. So to consider the net force part, there's another force that is acting on the object. It must be in the positive y-axis, equal to the one that's in the negative y-axis. That force, I don't know how much geometry you might have had in your life in the world of geometry. If something is coming out of a plane, out of a surface, directed perpendicularly to the surface, we call that normal. So that is the normal force, equal and opposite to the weight. So the weight of the crate, 10 kilograms times negative 9.8 meters per second squared, there is a force of negative 98 newtons acting on this crate, this box. There's also the normal force, perpendicular to the surface. It opposes the object's weight and is equal and opposite to the downward force. So it is a positive 98 Newton force acting on it. And then an object at rest tends to stay at rest. When you add those together, negative 98 newtons plus positive 98 newtons, you come up with zero newtons. There is zero net force. That means that the box sitting on the table is not accelerating. There's a way of looking at things. Chemistry is the science of how things change. A chemical reaction is a reaction in which chemical bonds are broken and reformed, and something is changing, fundamentally changing, typically, about a molecule that you're interacting with. And like maybe you have two liquids and you put them together, and then a solid precipitate forms out of that and sinks down to the bottom, and you're like, wow, I just, did something pretty cool there. Chemistry is the science of how things change. Physics, I know this sounds boring, but it isn't. Physics is often the science of how things stay the same. This box isn't moving, but we now have these tools to gain some insight as to why it isn't moving. And then maybe we can do something to start it moving, and we can make some assessments of what's going on there. So the science of how things stay the same. Hey, there's this dude on an elevator. The elevator is accelerating upward. The upward normal force exerted by the elevator floor on the person is larger than the downward weight of the person, identical to the downward weight of the person, or smaller than the downward weight of the person. So let us consider this. And I'm sad that we're not in person, because today is a day that I would hand you a force plate, which is essentially a scale, and tell you to go take a ride on the elevator. And wouldn't that be fun to ride up and down on an elevator standing on a scale? This human being doesn't look horribly enormous to me, but it says this person weighs 700 newtons. So this must be an enormous, massive, giant human being. So hold on. So here we go. Weight equals mg. So the weight is 700 newtons. So mass equals weight divided by g. So it says this guy weighs 700 newtons divided by 9.8 meters per second squared. 700 divided by 9.8 is 71.4 kilograms. 71.4 kilograms. So first of all, if you want to know how much you weigh using the metric system, you're probably going to report your weight in kilograms instead of newtons, but that's a mismatch, right? Mass is kilograms, weight is a force in newtons. So there's that. So this person weighs 71.4 kilograms. A kilogram is 2.2 pounds times 2.2. This person weighs about 157 pounds. So totally normal sized human being, but we're saying that they weigh 700 newtons, which sounds like madness. So just kind of keep that in mind. So what's going on here? Well, we're saying that there's a net force. When the person pressed the button to have the elevator go up, there's a net force. So what do we say? Net force equals mass times acceleration. That net force is going to be force up minus force down equals mass times acceleration. So the upward acting force, when this person presses the button to go up, and they're standing on the scale, and we can do this, at least at the very beginning, if you're on the elevator standing on the force plate that is reporting your weight in newtons, you press the button to go up, and the elevator starts to accelerate you upward. And it will instantaneously read 1,000 newtons. So 1,000 newtons minus 700 newtons. 1,000 newtons is pushing the person up. You're reading that from the force plate. 700 newtons is the true weight, the actual weight of this person, equals mass times acceleration. So acceleration equals, all that divided by mass, right? Equals 300 newtons divided by the mass. What did we say? We said 700 divided by 71.4, 71.4 kilograms. 300 divided by 71.4 is 4.20. Oh, press the button. I hate it when I press the button. Oh, make it stop. Okay, hold up. Still doing it. Clear all drawings. Close it. Annotate. Oh, come on. Oh. Sorry. 300 newtons divided by 71.4 kilograms was 4.20 meters per second squared. The net force in the y-axis as it's accelerating upward gives us an acceleration of positive 4.2 meters per second squared upward. Clear all drawings. Is that? Okay, now the person presses the button to go down. I don't know if you've ever noticed this. My son, who just graduated from Salem State in May, when he was a much younger child, he maybe didn't know all the smart things to do. And so when we went to an amusement park with our kids at the time, my wife took our daughter on one ride, and my 6-year-old son at that point didn't know enough not to trust me and agreed to go on Tower of Terror with me. If you've ridden on Tower of Terror or some kind of ride like that, it's kind of mimics an elevator ride, but the elevator will launch you upward. If you've ever gone up an elevator in a really tall building, there's significant acceleration and you can kind of feel like your knees bend when you press the button to go up, and it really launches you upward. And then Tower of Terror does this thing where it kind of accelerates downward faster than 9.8 meters per second squared. So you kind of lose your stomach and it falls out under you and then you catch up with it. That's kind of how elevators go down. Is it's not so much that the elevator motor is making the box go downward as it acts on you, but it's letting you fall a little bit. So here, the net force in the y-axis is always force up minus force down. And so the net force in the y-axis, the upward acting force is 400 newtons. That's what it reads on the scale, 400 newtons minus your true weight, 700 newtons. So the net force in the y-axis is going to be negative 300 newtons, which means mass times acceleration equals negative 300 newtons. And so the acceleration equals negative 300 newtons divided by the mass, 71.4 kilograms. This one is negative 4.2 meters per second squared. If you're riding an elevator in Meyer Hall, they don't necessarily match the up and down acceleration, but for this quick book example, we pretend they do. The other possibility is if you're in the elevator, you weigh 700 newtons, the floor pushes back on you with a force of 700 newtons, and then the cable snaps. When the cable snaps, the whole elevator car, including the floor, is falling downward with an acceleration of 9.8 meters per second squared. You too are falling downward with an acceleration of 9.8 meters per second squared. Therefore, as you plummet to your death or injury, you would look at the scale and see that during that time that the elevator is falling downward, you're weightless. That's all that weightless means, is that you're falling down, and as you're falling down, the normal force pushing back against you is negligible or zero. And so you're apparently weightless as that falls down. So ultimately, the answer to the original question, the elevator accelerating upward, is that the normal force exerted by the floor is larger than your true weight in order to overcome. So you step on the elevator, you weigh 700 newtons, you're standing there still, the floor is pushing back at you with a force of 700 newtons. You press the button to go up and you accelerate upward. Therefore, there's a bigger force pushing you up than the downward force that's holding you down. And so larger than. Okay. Is a net force being applied to an object when the object is moving downward with a constant acceleration of 9.8 meters per second squared? Net force equals mass times acceleration. Anything that exists has mass, so that's not debatable. An object has mass, and it's accelerating. Net force equals mass times acceleration. If this thing with mass is accelerating, then yes, there's a net force. That's the very definition of it. Is a net force being applied to an object when the object is moving downward with a constant velocity of 9.8 meters per second? If the velocity is constant, by definition, there's no acceleration. Acceleration is the change in velocity over time. So if there is no change in velocity, there's no acceleration. Therefore, there's no net force because there's no acceleration. So what? If there's no velocity, therefore there's no acceleration, does that mean that there's no force going on? There's no forces taking place? Whoa. This is one of my earlier PowerPoints, so you have to be nice to me. Whoa. So here in this tug of war, if both sides are pulling with an equal amount of force, there's no velocity, there's no acceleration, but there are two significant forces. There's a force to the left and a force to the right. They happen to be equal and opposite. So there's no net force. You can add up all the forces, and if it comes to be zero, then there's no net force. That brings us to Newton's third law of motion. I know this is a lot of stuff kind of coming fast and furious, but you gotta just kind of take this in, we'll use it, and then we'll move on to the next stuff a little bit later. Whenever one body exerts a force on a second body, the second body exerts an oppositely directed force of equal magnitude on the first body. Just kind of push anything, push the wall, lean against the wall. You're applying a force, it's applying a force back on you. You can feel it. Toss a ball. When you're throwing the ball, you can feel it pushing on your hand even as you are pushing it forward. Whenever one body exerts a force on a second body, the second body will exert an oppositely directed force of equal magnitude back on the first body. That doesn't preclude motion, right? Like I have a ball and I'm going to throw it. As I go to throw it, I'm applying a force, the ball's applying a force on me. I am so much more massive than this ball. I have the strength to throw it. I can make the ball move, but the ball's still pushing on me as I push on it. So the astronaut is pushing on the space station with a force of 10 newtons. Do they both experience, both the astronaut and the space station, do they both experience the same force? Do they both experience the same acceleration? And so there's the thing, like when you know, is this intuitive or counterintuitive? You know that it's not the same. This astronaut maybe has a mass that is at least an order of magnitude smaller than the space station. So the force is the same. If the astronaut pushes with a force, I forget what I picked for numbers here, they push with a force of 10 newtons, then the space station pushes back on the astronaut with a force of 10 newtons. However, the astronaut, 10 newtons for their 100 kilograms of mass, would experience an acceleration of 0.1 meters per second squared, whereas the space station, if it's 10 times more massive, would experience an acceleration of 0.01 meters per second squared, much smaller acceleration. Same force, smaller acceleration. The force itself only exists for the length of the arm of the astronaut pushing on it. So if they push with a force of 10 newtons, this whole acceleration event will occur only for the duration, the arm length of the astronaut. And from then on, it would be constant velocity. So, taught this course in a number of different ways. If we were transitioning right now to the next chapter, we would be reviewing these applications of Newton's laws and then starting to use them in a bunch of ways. Right now, we'll just, kind of summarize Newton's first law of motion. Object continues in a state of rest or in a state of motion at constant speed in a straight line, unless it's compelled to change that state by virtue of a net force. So what happens if you have a net force? When there is a net external force that acts on an object of mass m, the acceleration that results is directly proportional to the net force, bigger acceleration, and inversely proportional to the mass. Same force, bigger mass, less acceleration. The direction of the acceleration is the same direction as the net force. So F equals ma, you've probably heard of that. And so the unit for force is newtons. Kilograms times meters per second squared is newtons. Whenever one body exerts a force on a second body, the second body exerts an oppositely directed force of equal magnitude back on the first body. Those are Newton's 3 laws of motion. Out of these 3 laws, we really only have this one equation with 3 terms. So it's pretty easy to use, but we will always be building on the foundation of kinematics. So we will go back and use those kinematics equations. So typically you use the Newton's second law force equation to gain some insight into the acceleration. And once you have that acceleration, you would use the kinematics equations. So let me point out chapter 4 homework is not too brutal. 1, 2, 3, 4, 5 questions. Some of them are very straightforward. A 63 kilogram sprinter starts a race with an acceleration of 4.2 meters per second squared. What is the net external force? Force equals ma, m, a. That's really straightforward. Problem 2 is kind of a kinematics question, right? So they're going to accelerate for 20 meters, and then for the remaining 80 meters, they're going to go at constant velocity. So it's 2 different problems all in one. First, you're going to figure out how much time it takes if you're accelerating at 4.2 meters per second squared for a distance of 20 meters. You figure out how much time that was. And then you also figure out what the final velocity is at 20 meters and use that velocity for the remaining 80 meters and figure out that time. Add them together. The rocket sled, you have multiple forces. It's going to accelerate at 49 meters per second squared. The passenger has a mass of 75 kilograms. Part of it is straightforward, easy, 49 times 75. It's a horizontal component. The weight, this person has a mass of 75 kilograms. Therefore, they're accelerated downward, 75 times 9.8. And so you're going to figure out what's going on compared to the weight. The rocket that is accelerating upward has mass, therefore has weight directed down. It has another force directed upward and another force that is air resistance directed downward. The net force is going to involve the sum of all the forces. There's multiple downward forces, one upward force. You add those all together, the vector sum, positive plus negative, and you come up with a net force, and then you figure out the acceleration. And this one is kind of like the most important thing ever when we resolve a vector into its components, because we are not leaving that behind. As you tackle the chapter 4 homework, don't forget to take another peek. Make sure you get through the chapter 3 homework. Chapter 3 homework will be the foundation along with the football question for the quiz on Wednesday. So make sure you understand these questions, watch the videos. If you have questions, email me. If you have questions, set up an appointment if you want to do that. The quiz on Wednesday is on chapter 3 material. So prepare for that. You can do that at your leisure. It doesn't have to be right now or, during class time. And then it's not too early to start thinking about the exam. I have the practice exam posted to our Canvas page. I will give you all the equations you need. The point of the course is not memorizing equations. I'll give you all the equations you need. And then just kind of take a walk through. I would recommend try to do the practice exam as though you were doing the real exam. The practice exam has 20 questions on it. The real exam will not have 20 questions. The practice exam is a little more extensive than the real exam is. There is some stuff on the practice exam that we haven't talked about yet because we have the material from Wednesday's lecture. But once you get through that, you should be able to answer these questions. If you're able to answer these questions without too much of a challenge, then you should be in really good shape for the real exam. The real exam is not identical to the practice exam, but it's another exam that I produced. You should, it's the kind of questions I ask. So go work through the practice exam. When you have worked through the practice exam, then I'd say go ahead and look at the key. You look at the key to the practice exam. You will find my way of answering the questions. You don't have to answer every question exactly the same way that I do, but make sure you get the right answers. And here's an example of me walking through those answers. If looking at the answers on a piece of paper isn't enough, there's a video walkthrough of me walking through the practice exam that could hopefully be helpful to you as well. That's all for the exam that is next Wednesday, a week from Wednesday. So you have plenty of time to get through that. So that's all we have for chapter 4 today. I will post the video of this meeting here as soon as it's ready. I will post the video of the chapter 5 lecture as soon as I find it and put it on there, but I'll have a lecture video for chapter 5, the football question, and then the quiz for you whenever you want to do it. But if you want to do it during class time on Wednesday, that's a fine idea. I will not be here for class time on Wednesday. I will be at a long meeting. So we will gather together again 1 week from today on Monday, and we'll see how you're doing, and maybe we'll push ahead a little bit into more material, but we'll definitely review any questions you have from the practice exam so that you are ready for the real exam on Wednesday, June 16th. Whew. Okay. Any questions before we part ways today? Hearing none, seeing none, I will wish you a happy day. I will stop recording.